Greetings and welcome to the third unit of second week. It is on program outcomes, PO3, PO4 and PO5. And we explored the features of program outcomes of PO1 and PO2 in the last unit. We will now try to understand the features of program outcomes PO3, PO4 and PO5. PO3, what does it say? Design development of solutions. Design creative solutions for complex engineering problems and develop systems, components and processes to meet identified needs with consideration for the public health and safety. Whole life cost, net zero carbon, culture, society and environment as required. As you can see, it's a tall order. You are talking about whenever you are doing a design, you are supposed to consider the requirements related to public health and safety, whole life cost of the component or system, net zero carbon, culture, society and environment as required. I don't think any of the existing programs are ever doing any design taking any of these things into consideration. So it requires everyone concerned with engineering programs to take a fresh look at their program as well as courses, how to address these aspects in whatever they are doing. Designing solutions for engineering problems can only be experienced through projects and assignments. And these are time-consuming activities and hence cannot be included in limited time written examination. In a limited time exam means your class tests are final exam, end semester exam. These end semester exams and tests have their own characteristics. They have to have a number of problems, and a number of problems means the amount of time a student can spend on each problem is limited. And if it is limited to, let us say, a maximum half an hour to a problem in a 3-hour exam, you cannot ask questions that will try to provide creative solutions to complex engineering problems. It is not possible. And fortunately, these days, programs have many institutions have come around to having something like 50% for internal evaluation and 50% for the end semester exam. Sometimes some private universities have gone even to 70% weightage to the internal evaluation, only 30% to the final exam. But then the internal evaluation cannot be again restricted to 1 hour, 1.5 hour tests. They have to be should be given to assignments. Assignments can be very detailed. They can carry more marks, but then they have to be orchestrated. That means the rubrics that you use to evaluate the assignments should address many of these aspects. Okay. So that will come later in another course on assessments. Components of systems can be designed through smaller assignments in some identified courses. So at least you look at smaller assignments in a few agreed upon identified courses, and this design takes place with respect to that. The design criteria and specifications of components and processes need to be evolved from the solutions to a given problem. That is, you are given a problem, you first identify how you are going to solve that. Depending on how you want to solve that, you have to identify the criteria and specifications of components. They have to evolve from that. Nobody gives you that. These criteria and specifications should be developed taking issues related to public health and safety and the cultural, social and environmental consideration. Can you justify how you came up with these specifications? And that is a fairly, what do you call, is a challenge to incorporate that into a course at the course level. Issues related to public health, safety and environmental consideration can be addressed through design using relevant standards. Generally, the standards are, when they are evolved, a large number of professionals spend a lot of time to come up with these standards, and the standards will help you. Each faculty member doesn't have to develop these standards. Somebody has developed, you have to understand and say which standard is applicable to your part of the design and what is involved in actually meeting that standard is what the faculty member will have to explain to the students. Cultural and social considerations will require inputs from non-engineering fields and get incorporated into both functional and non-functional specifications. There are some functional specifications like what kind of input constraints, what kind of output constraints, and what specifications it should meet. Non-functional means so-called industrial design of those components or products, how to meet them. They are not functional part of it, non-functional. That means the form of the product, the way it looks, the way it is held. For example, if you go to market, when you are trying to look for selecting a product on the shelves, let's say functionally they all meet your requirements, but for some products you like, some you don't like. And that is what constitutes what you call non-functional specifications. Here are some examples of standards. This is not an exhaustive list. You have to find the relevant standard and work within that. For example, road vehicles functional safety, ISO 26262, that is relevant for mechanical engineers if they have courses on something related to any automotive vehicles. Okay, if you are doing that, there are courses included in the program, then the standard will have to be met. That's what it means. Okay, I will not try to go through each one of them separately. Now, what are the activities through which you can address PO3? Understand the role of public health and safety and environmental considerations in determining the functional and non-functional requirements of products and processes. Can you take some examples and look at it from these considerations: public health, safety and environment. Understand the role of cultural and societal considerations in determining the non-functional requirements of products and processes. Identify the standards that are applicable to the product or processes that needs to be designed and developed. Okay, you have to identify which standard is applicable to you. Design components and subsystems as per specifications. Specify the testing process to check the performance of the designed product or process. Document the design of products and components and processes. If you are able to go through all these steps, then you are meeting at least some aspect of PO3. Some samples: develop and test prototypes of mechanical devices ensuring they operate safely under various conditions and meet regulatory requirements. Here, this is an umbrella type of statement. So, you have to, if you want to convert into a specific activity, you have to identify which mechanical device that you are trying to develop. Under what conditions are you need to operate safely, and what regulatory mechanism you have to meet. So, you have to become specific. To that extent, it can lead to a large number of problems that you can bring into the classroom. Design components of a smart electrical grid that enhance reliability and safety while incorporating renewable energy sources considering socio-economic factors. That's a fairly vast one. At least some aspects of that can be brought as assignments in a course, specifying all the constraints under which you want the student to solve the problem. Another example: create safety protocols and devices like circuit breakers or grounding systems that prevent hazards considering local, cultural and societal contexts. Some more samples: design systems for safe drinking water that cater to local community needs considering cultural aspects and environmental health. Okay. So, these are the kind of samples that you can make use of in a particular branch, or you have to select from this. Now, coming to PO4, conduct investigations of complex problems. Conduct investigations of complex engineering problems using research-based knowledge, including design of experiments, modeling, analysis, and interpretation of data to provide valid conclusions. You have to pay attention to WK8 when you design your specific course outcomes. Now, to elaborate this, use research-based knowledge to provide valid conclusions. Most of the core courses do not generally provide such learning experiences at all. It requires collection of a set of research papers that can be understood by the UG students and posing a set of questions. That requires certain amount of a lot of planning by a group of faculty in identifying, because you cannot actually do all the experiments in the class. At least you bring some research papers together, put them together, make them accessible to the students. Now these days it is possible to do so on create a website for the course, and then you can ask them to, you pose a set of questions to them, and so that you can make them reach some valid conclusions. Understand the research methods relevant to the discipline of concern. Okay, which are the research methods that you have to use? And it will become difficult to design and implement such exercises, particularly at undergraduate level in majority of the institutions. The only thing that possibly you can do, research method of design of experiments can be experienced through some open-ended experiments in some laboratories. At least, though you have to have closed type of experiments to understand how to make use of the equipment, how to operate that, how to take measurements, but you can have a few experiments. For example, any course can have something like 12 to 14 experiments, in that at least 2 or 3 can be open-ended experiments. What they are, how to plan them, how do you implement, that requires planning by the faculty of the department. The research method of analysis and interpretation of data and synthesis of information requires collection of significant amount of data related to context and posing questions that can lead to synthesis of information. Such context can more readily be identified in subjects like databases, material science related subjects, chemical process optimization, nanotechnology, and device and sensor design. And sometimes the data can be obtained from some research papers and ask the students to just analyze the data. And you can have some activity where only you collect the data. So the student has to experience all these phases, not necessarily to the same problem, but on different problems in different ways. At least if he is familiar with all the aspects, then he will be able to concentrate, let us say, in a project or in a mini project or a major project. He can go through all the phases of this, of PO4. So PO4 activities: plan and perform experiments, surveys and collect the data in accordance with the applicable standards. Perform the necessary calculations and data reduction to draw valid conclusions. Present the results in a professional manner. These are the activities that you can incorporate into some courses. Now some samples. Conduct experiments to study the effects of different variables on material strength, analyzing results to optimize material selection. Collect experimental data on heat exchangers or engines, analyze performance metrics and synthesize findings to improve efficiency. In electronics, implement and test filters or algorithms, analyze outputs and synthesize results to enhance noise reduction or data clarity. These are all potentially possible provided first if the faculty are convinced that these need to be included, and then it requires considerable amount of planning and preparation to incorporate such issues. Some more samples. In civil engineering, research soil properties through experiments, analyze geotechnical data and synthesize findings to advise for foundation design. In computer science, conduct experiments to evaluate efficiency of new algorithms, analyze computational time, accuracy, memory requirements and synthesize results to optimize code. Coming to PO5, it is engineering tool usage. The statement says, create, select and apply appropriate techniques, resources and modern engineering and IT tools, including prediction and modeling, recognizing their limitations to solve complex engineering problems. It should address WK2 and WK6. So here if you look at, this is related to creating, selecting and applying modern engineering IT tools. That is one part of the PO5. Creation of tools can only be attempted through projects, preferably by multidisciplinary teams. You cannot create a usable modern tool. Neither you can design and build nor develop an IT tool to do that. That can only come through a project. That too multidisciplinary teams that have to be involved. The other thing that can be done is selection can only be at a paper level, comparing different tools for specified application. You can give an exercise to students saying that you have in the market about half a dozen tools. for performing something, you can ask them to compare their performance and ask them to justify why they should select one. That exercise can be given. Selection can only be limited to that. Right now, many institutions incorporate IT tools into their laboratories. Modern measurement and testing tools are very expensive and very few institutions can afford them at undergraduate level, but virtual laboratories can provide an avenue if you are interested. Complexity in engineering is characterized by large number of variables, phenomena with widely different time constants, presence of noise, independent multiple decision making, and our systems with a number of negative and positive feedback loops. That is how complexity in engineering is characterized. Now what you can do is, by looking at it, you can say whatever tool that you are using, what aspects can it actually look at it. If an exercise can be planned, at least the students will get exposure to that. Prediction of behavior of complex engineering systems requires a wide range of modeling methods and their simulation. Do you have system level modeling course and simulation of that? To my knowledge, I don't find any program that at least I haven't come across examples where complex engineering systems are modeled at systems level and or they use any simulation methods or tools to actually simulate. It is doable. There are tools available, not very expensive, but you have to look at a complex system and model it. Modeling can form a course actually. While modeling is a part of a number of engineering courses, simulation can be extensively used at classroom level and in laboratories. That is one thing possible in today's context. You can acquire some simulation tool and actually demonstrate in the classroom how, when you have a large number of variables, changing some variable, what happens to the system and so on. And to address PO5, what are the activities? Some activities, these are some examples. It is not, you need not limit it to this. Determine the requirements of a simulation tool for a class of engineering problems. Create tools for simulation and solving a class of engineering problems. Select the most cost-effective tool from the commercially available engineering and IT tools for addressing a class of engineering problems. Understand the limitations of a given engineering or IT tool. Sometimes if the tool is applied to in a wrong situation, you can come with kind of a funny type of conclusions. So you have to be very careful what is the limitation of each tool that you can apply. Use the engineering IT tools made available by the departments. Some samples of PO5. Use CAD software to design mechanical components or systems, applying modeling techniques and understanding software limitations in representing real world physics. Utilize software like SPICE to simulate and analyze electronic circuits, determining the performance under different conditions and understanding the accuracy limits of simulations. You can design. SPICE is made available by majority of the institutions, but you have to extend the application to understand what are its limits to which you can apply. If you try to draw conclusions when the variables are out of certain range, then the conclusions cannot be accepted. So people have to explore that where exactly they have to stop applying this. Program microcontrollers to control devices, applying real-time operating systems and learning about the constraints of processing power and memory. So similar examples from other branches can also be used. I will not read through all of them. So in the next unit, we will try to understand the features of program outcomes of PO6, PO7 and PO8. And thank you for your attention.